Hi everyone, welcome back to another bandwidth audio video. Today we're covering something a little bit different than what we've been doing recently, which has been the 2845 videos. Here I wanted to talk about a new piece of equipment we got in, the Hickok Model 700 Dynamic Mutual Conductance Vacuum Tube Tester. So this is quite a big, heavy piece of equipment that's really been found itself right at home at the shop here. Has been really useful for us for testing and matching large output tubes for our power amplifiers. So this unit, when we got it, was actually not working. Looked like it wasn't hadn't been in use for quite some time, and so our job was to get this up and running. And a couple of things that were wrong with it. First of all, were a couple bad meters. So this meter here, which is the grid bias voltage, this is a replacement Simpson meter for the Hickok meter, which is broken. You can see the needles just kind of moves around a little bit, but it's just kind of floating around in the case there. And then the other meter that was broken was the filament voltage meter. So we actually had to get a custom replacement made that has the 3 different scales on it, which correspond to the filament adjustment knob or range adjustment knob here. So that's another custom meter. Other problems with this were, resistors out of tolerance, which is pretty typical of a piece of equipment from this era. As well as failed power supply capacitors. So in the power supply, these were the capacitors that were in it, and this box is probably like 18 pounds of capacitors, and these are paper and oil film capacitors, where the film is actually paper. So these are 10 microfarad 600 volt DC capacitors. These were all bad, and these caps actually use PCB oils, which is a chlorinated or polychloride, some nasty chemical. I don't remember what the B stands for, but it's a biohazardous chemical. And actually, you can see this capacitor, this one's okay. This is a more recent replacement. You can tell it doesn't match the other ones, which were those Astrons. The reason being is one of the capacitors clearly had failed. So where this was positioned in the power supply back in the unit down in here, there's a big kind of stain where clearly the residue from that PCB oil leaked out of one of these capacitors. And so I actually tested these with some decently high voltage as well as just an LCR meter. And if I just squeezed the can just by a little bit, the capacitance would change by over 100% on all of these. So these are all really bad, not good. So to fix that, I had to build some turret boards and mount modern electrolytic capacitors, and I used 2 in series, 222 microfarads in series for every one of those bad 10 microfarad capacitors there. So I had to build a custom turret board and get that mounted in the power supply. We had to get some new vacuum tubes for the power supply and make sure everything was up to snuff there. And then one of the other issues we had was actually a broken wafer switch here for the tube voltage range. And so this switch is a wafer switch with I think it's four wafers, and each wafer has two sides, a top side and a bottom side, with different contacts and different switching poles as you turn the switch. And so there's basically, the switch has 8 different pole decks. So it's actually quite complicated, the switching arrangement of this. And 2 of the wafers, so 4 decks, or 2 decks, 4 poles essentially were broken off of the wafer switch. It got smashed from the backside and cracked. And so we had to kind of work through schematically how that switch was wired to figure out how to make a workaround, because you can't get these types of wafer switches with the the super specific switching arrangement that Hickok put into these. You can't get those anymore. And actually, funny enough, the wiring around the switch was different from the published schematic for this unit. It's not wrong, it's just different, and so that took us even longer to figure out why the switch, the way we were reconstructing this broken switch, why even once we reconstructed it, didn't make sense relative to the schematic. So it took a little bit of time to run that down, but we got it working. These two toggle switches replace the function of the broken wafer, and one of them is a simple on-off for the filament. So as you rotated this switch off of the off position, or from the off position to one of the voltage ranges, it automatically then turned on the filament. And then the second one is the position of a high power resistor relative to this voltage adjustment, filament voltage adjustment rheostat. So depending on this switch range, there would be a resistor either on the high side or the low side of that rheostat to change the adjustment range in order to get the full adjustment range of voltage depending on your tube current. So that took a little while to get all sorted. But it is working. It's working extremely well. We've already put this to good use and been matching tubes on it now for a couple months. But I guess I can talk through its operation and kind of the overview of the panel. Starting out at the bottom left here, we've got our plate voltage supply. So we've got an adjustment knob to adjust the plate voltage, and then we've got a range switch, which is low, medium, or high, and then another range switch, 0 to 30 or 0 to 300 volts, which scales the meter. So you've got a range switch that scales the meter independently of the actual output voltage. And again, it's interlocked. That's what it's kind of warning you about here. It's interlocked such that if you go to 30 volts and you're in the high mode, it automatically reduces the voltage so you don't blow out this meter. But that's the plate section, fully adjustable, 300 to 300 volts. Screen supply next is very similar. Same meter, same knob, and then same two range adjustment switches. So both the plate and the screen are completely adjustable from 0 to 300 volts. And what's really nice about this tester is these these power supplies are actually regulated. There's a linear vacuum tube regulator that adjusts the output voltage to the vacuum tube under test and regulates it regardless of the current drawn by the tube. And this is what sets this tester apart. Whenever you look at these big vacuum tube analyzers like this, there's a Weston, I think 686 tester that's often referenced when you're talking about these Hickok Model 700s. The Weston looks very similar. It's got all the meters. It can do, measure a wide range of parameters, but it's really primitive and simple because none of the power supplies are regulated. It's just a linear supply with no regulation, unlike the Hickok, which is fully regulated. And that's really nice because once you set this up for a specific vacuum tube and you put a tube in the patch panel up here, you don't need to adjust any of these knobs once you get your test conditions set up, even if the tube performance is wildly different. And wildly different all the way from an open circuit to, the full 200 milliamp scale that this can measure. So that's extremely nice with this tester and makes it super repeatable. We've had great repeatability results with something that's, old and analog like this. So moving on anyway, the bottom right here, this is our bias voltage or grid voltage supply. And this is also regulated. We've got our adjustment here and then two ranges, 0 to 10 volts or 0 to 100 volts. The grid voltage can also be set up to be either negative or positive, depending on the type of test. Now, although this is regulated, it's not designed to be able to source a lot of current. So you can't use the positive grid voltage to drive tubes into their grid current region. That's just not what this is designed for. And that's fine. That's not the point of us having this tester anyway. But it is interesting that you can switch the polarity. Along with that, changing this meter, we've also put in a multi-turn bias adjustment knob. So it's a 10-turn adjustment pot to give you much finer control in either the 0 to 10 volt or 0 to 100 volt range, because small changes in the bias setting have large implications on the current and the transconductance. So we want to be able to make sure we can repeatedly set this up repeatedly and in a repeatable manner to our desired voltage to test under. So that's the bias section. Next, we get up to kind of the grid control or grid signal section. So in series with the grid, we've got a microammeter that can read both positive or negative grid current. So we can check for things like ionization or cathode material that's gotten deposited onto the grid. And then here we have our grid voltage range. So there's a separate transformer from that's powered off the AC mains that has different taps to drive different grid voltages in series with that grid power supply down here. So we can superimpose our AC test signal in series with the grid. And that voltage range is adjustable. If we've got a high gain tube, we don't want to put 1 volt RMS on the tube that's, got a gain of 100, like a 12AX7 or something. We want to put a much smaller signal. So that's adjustable. And as you adjust the grid voltage, you also need to adjust the scaling of the transconductance meter such that you're reading in true micromhos or milliamps per volt. You don't have to do any funny scaling if you change your grid volts. So there's a little plate here that tells you the different combinations of signal volts and that range selector knob over here to get the different full scale in micromhos on this meter. And micromhos, by the way, is just a different name for transconductance. Modern MOSFETs will use amps or milliamps per volt. Micromhos is milliamps per volt just multiplied by 1,000. So that number there, 10,000 micromhos is 10 milliamps per volt. It's the same thing. There's another winding off this signal transformer that drives this meter. And so the winding is only dedicated for driving this meter. And what it does is it allows you to see what the output voltage is independently of the signal voltage. So you don't load the grid. You're not doing anything different from the tube under test, but you can at least monitor basically the signal generator independently by using this auxiliary winding on that same transformer. And that allows you to standardize the line. So what they mean is, like, if you've got AC voltage variation from your mains, you can set this needle up to that midpoint every time, and you're going to get the exact same drive signal into the grid of the tube to check your transconductance. So it's really elegant, really simple, and extremely repeatable the way this is designed. And then at the very top of the tube tester, we've got our filament current on the right here. So this is an ammeter that uses a current transformer actually in series with the filament wiring of the tube tester. So there's a little very low ohmic, low resistance transformer that then separately drives this meter and samples basically the current flowing through the primary of that transformer to drive this current meter. And then a voltmeter, which is not quite Kelvin sensed up to this panel, but it's pretty darn good. It's pretty close to accurately measuring what's happening at the tube socket with just a little bit of voltage drop. So it's not too bad. Moving up to the patch bay, this tester has switches for every internal electrode to switch to different vacuum tube pins on the sockets up here. Unfortunately, 2 of these wafer switches are broken, which renders this entire switch bank non-operational. And the reason is these switches are actually interlocked. So for example, like if I had the plate on pin 1 and then selected screen pin 1, these 2 power supplies would be connected directly together, and you'd break something in here if their voltages were just set up dissimilarly, right? You pushed whichever one was higher would push current backwards into the other supply. That's no good. These switches actually, it's really neat. It's really clever. It takes care of that for you such that I can never connect the screen or plate together electrically, even if I select them the same here. But because of that, every single pin on the wafer switch is wired to the same pin on every one of these patch switches. And so if any one of these wafers breaks, you can't use any of these switches. And that's unfortunately what's happened. Luckily for us, the Hickok in their infinite wisdom, foresaw some problems maybe with that arrangement, or thought maybe you'd want to do something custom, and they put a patch bay here. So these are just standard banana cables, and we can connect, all the internal electrodes to any of the pins, pin 1 through 12, on any of the sockets up here on the top panel. So luckily, even though those switches are broken, we've got a perfectly good workaround. And actually, this is preferred because the impedance or resistance of all these interlock switches with their long wiring, connecting them all together essentially, is not the best for accurate testing. So that's okay, but thought it was worth mentioning. So with that, let me power on the unit. The unit came up. We can see our line adjust is reading correct. It's right in the middle. And there's a time delay from power on to when the high voltage rectifiers get switched on. So in a couple seconds, you'll see these meters come up, and it's allowing the filaments of all the tubes in the power supply to warm up. And there you go, you can see it, they just came up. And I've got this set up at approximately 250 volts for the plate, 250 volts for the screen, and we should be about 15 volts for the bias, although like I said, I was messing around with that knob a little bit, so we'll set that accurately in a moment. My goal here today is to test a couple different KT88 tubes we have, and I'm doing this live with you for the first time. But with the KT88 from the data sheet, with 250 volts on the plate, 250 volts on the screen, and 15 volts on the grid, we should get 140 milliamps of plate current, approximately 3 milliamps of screen current, and a transconductance of 11.5 milliamps per volt, or 11,500 micromhos based on that meter. So that's what we're going to test, and this is how the factory tested these tubes, and this allows us to test and match KT88s directly to the factory recommended test conditions. And again, these are real-world conditions. They're known and repeatable with this tester, so we have really high confidence that when we match to this, we're testing and matching accurately and matching the tubes when they're operating at a static, hot operating condition. So before we plug in a KT88, first thing I'm going to do is turn on my multimeter here, and what I'm going to do is just confirm I've got the bias set correctly. Although these meters are accurate, and in fact actually I've calibrated all these meters as a side note. Luckily all the meters in this unit read high, and meters reading high is great because it allows us to modify them to read correctly with a resistor. So for example, this ammeter read a little bit high. I put a series, shunt resistor in parallel with the meter movement to shunt a little bit of current away from the movement, which allowed me to bring the measurement back into like perfect spec for the meter. Similarly for the voltmeters, these also read high, which allowed me to put a series resistor and drop series voltage before the voltage reaches across the movement. So for example, if like this plate voltmeter read 10 volts too high, I could put a series resistor such that I drop 10 volts across the series resistor before reaching the meter, and then the meter will read correctly. So I've taken that step on all of these meters. But again, it's nice to have a little bit of confirmation with a DMM, especially with regards to this bias, because there's so much sensitivity. And I've got future plans, and actually you can see down here, I've got future plans with these digital meters where I'm going to make a little box and take advantage of these extra jumper positions and do a digital meter panel, kind of a sidecar panel that will monitor all of the voltages digitally, as well as having these analog meters down here. So we've got this roughly set up. Right now our patch bay is cold until we push this button, which is the connect button. So tube element potentials, we push connect, and now we get all of our voltages to the patch bay. So we're close to our 15 volts, we're a little shy, so I can adjust this up slightly. .01 or approximately 15 volts, that's plenty good. So we've got our 15 volts of grid bias. Now let's check the screen and plate voltage and make sure those are okay. So screen voltage should be 250 volts. We're right there. And then plate voltage should also be 250 volts. 251. Now I've been using this tester enough to know that the plate voltage should be set just a little bit higher open circuit. Because the plate pulls more current than the screen, there's enough wiring resistance from the power supply to the patch panel to drop a little bit of voltage when a vacuum tube's actually under test and pulling current. So with a KT88 pulling 130 to 140 milliamps, it's about 1 volt drop from the power supply output to the actual tube socket. And so I'm just accounting for it there with that extra 151 volts rather than an exact 150. And then the last thing we'll check is the filament voltage. So we patch into that, turn my voltmeter to AC mode, and then switch on the filament voltage, and you can read it there. And we're a bit high. This should be correct once we plug in an actual tube, because right now the filament the filament transformer is completely unloaded. So we're just measuring the open circuit voltage of the transformer. But once we start pulling our 1.5 or 2 amps, whatever the filament current is for a KT88, it'll drag down that voltage a little bit based on the winding resistance of the filament transformer. So we seem pretty well set up. Let's turn off the filament to start. Let's make sure we don't have any high voltage present at the tube socket when we plug in our tube. And we're ready to go. I guess before I plug in a tube, one thing I should mention is tube testers like this are typically troublesome because you need to sequence your power supplies. So if we set up, for example, our plate voltage onto our tube before we set our grid voltage, the tube's going to be running flat out and we can burn out the tube. Similarly, if we set up our screen voltage, even if a grid voltage is present, if we set up our screen voltage before the plate voltage, the screen, since it's will be the highest voltage element in the vacuum tube, will take all of the power that would normally be dissipated in the plate, and you'll destroy the screen. So normally with a tester like this, and I think the Weston I mentioned before is like this, you have to sequence these power supplies very carefully when you actually have a tube in that socket. With this tester, there's no need for that. We can set up these in any order we want because we've got this one switch here that we can push once our power supply is set up to then push push all the voltages from the test panel here, the measurement panel, up to the socket over there. So this gives us really great freedom to set these up as we need, get confident that we've got the right operating conditions, and then just push all those power supply voltages over to the socket once we're ready. So you'll see that in action. So here's one of the KT88s. This is from our friends at Tube Depot. And I think these were purchased for actually a personal project, and these have a number reading of 44 on them. So 44 what? I don't really know. I think only Tube Depot does. So here, let me install this tube. And that's the point. If Tube Depot tests 44, the question is well, what was their test condition? If I buy more of these KT88s and they have different numbers on them, what do they mean? How do I know they're accurately matched? And that's what this will tell us. And we can get perfect match pairs or quads or sextets of vacuum tubes with this tester. So we've got that tube with whatever the number 44 on it as Tube Depot's matching number. We can turn on the filament. We see the current come up and then actually drop back down as the filament heats up and the resistance of the filament grows. and we could see our filament voltage climbing up. So it's a little bit low, because I was playing around with that, but I can turn it up and get a little bit closer to the target 6.3. There we go, 6.28, 6. Yeah, we're right there. That's perfect. So we've got the filament voltage, the tube's warming up. What I'm going to do is just move our multimeter back to measure the grid voltage. I like just to make sure the grid's not moving around. Not that it does with this tester, but just because all the performance metrics are so sensitive to the grid voltage. So we should be set up and ready to go. When I push the connect button, we should see the plate current on the 200 milliamp scale. We'll see the plate current come up. There we go. So we're at 130 milliamps. It's stabilizing about 130 milliamps of plate current. We could check the screen by turning that to screen and then going up onto the higher scale. We've got about 13.5 milliamps of screen current. So that seems pretty reasonable for a new production KT88. Those numbers are about what we've seen before. So let me go back to the 200 milliamp scale and go back to the plate. So the tube's nicely warmed up. Our bias voltage is still 15 volts, as it should be. Now with the push of this button, we can apply our grid test signal. And now you gotta tap the meter a little bit. These old meters are a little sticky, but it is very repeatable. Just give it a few gentle taps and we can get our transconductance. And we're right at 10,000 micromhos, or 10 milliamps per volt. So 10 milliamps per volt and 134 milliamps. And that's it. We then release our signal, release the voltage, the ammeter dropped, and then turn off the filament. And that's it. So we've just tested one tube. This tube's quite toasty now because we were operating it at a decent operating point. So let me try to get that back. We can take another one. So this is another tube from Tube Depot, number 42. So again, what that means I don't know, but maybe it'll mean something. Let's test it. Plugged in, filament on, filament current's falling. So the filaments has good health, the current's in range. Apply our high voltage. And because the filament is probably still warming up, we should see the current come up. Yeah, there. So we're watching the plate current rise real time. So it's still growing. 134, 136. Looks like it's still growing a little bit. Looks like it's probably going to stabilize around 138 milliamps. So this tube's definitely drawing a bit more current than the previous one. And let's test the transconductance. So we got to make sure our needle gets zeroed. And then put in our signal. So there you go, this tube is stronger in current and stronger in transconductance. So this one's closer, actually right on the money for the data sheet. It's 11.5 milliamps per volt, or 11,500 micromhos. If we release it, goes back to 0. Release our high voltage. turn off our filament. And that's it. So yeah, this is a great piece of equipment, a great addition to the Bandwidth Audio shop, and is now a permanent part of kind of our production test flow, or at least our test flow when we get new vacuum tubes. We'll run them all through this, or I should say power tubes at least. Our power tubes we're going to run through this permanently. We're going to test them and match them all and put them into our amplifiers. And so far we've had great results with that. We've been getting better performance when we test them on this, especially for our push-pull output stages, because we can get them to match so tightly on a tool like this. So I hope everyone found this useful and enjoyed the video. I'll talk to you soon, and take care.